man's ability to drive an automobile has limitations beyond which he dares not go. Automobiles have been built to travel at higher and higher speeds, but our own physical limitations, plus the natural laws of friction, centrifugal force, gravity, and kinetic energy, all combine to prevent us from exceeding speeds which violate these natural laws. Violation of these laws brings immediate punishment. It takes time to move. Even the quickest move you can make requires time. This machine, called a reactometer, can measure in hundredths of a second your reflexes, or the time it takes your eyes to see, your brain to order, and your hands or feet to carry out. This test presents a very simple situation, and the average reaction time is about 1/2 second. Under actual driving conditions, your reactions are not quite so simple. You may have to choose between several alternatives and pick the right one while your attention is focused on driving the car, hazards ahead, and conditions around you. This is called complex reaction time. Under these situations, you will require from 3/4 to 1 second to react. This device, called a brake reaction detonator, measures reaction time in distance. The detonator is hung on the front bumper. The person making the test fires the first cartridge, making a mark on the street. At the sound of the explosion, the driver applies the brakes, causing the second cartridge to discharge, making the second mark on the street. This distance, 22 feet, is how far you travel at 20 miles per hour before you can even begin to slow down your car. At higher speeds, of course, the distance is proportionately greater. In addition to our physical limitations, there are natural laws which work automatically and are inescapable. Let us first consider friction. The entire control of a moving car depends on the grip which 4 small areas of tire surface, each about as big as the palm of your hand, have on the road. This grip is called friction. The friction between the wheels and the pavement enables the car to start, stop, and keep moving. Friction plays its part when your car is rounding a curve, but there is also another force at work. This is called centrifugal force. A moving object tends to keep moving in a straight line. A rock whirled on the end of a string is pulled from a straight course by the tension of the string. If the string should break, centrifugal force would cause the rock to fly out into space. The same law holds true when an automobile rounds a curve. At a safe speed, the friction of the tires on the road surface does the same thing that the string does to the stone, holds it in its curved path. If your centrifugal force is increased by additional speed, your friction bond will break. The car will skid off the road. The amount of friction between tire and roadway depends on the condition of the tires and the condition of the roadway. Wet or icy surfaces can increase your chances of skidding as much as 10 times. At high speeds, even on the best roads, the force pressing against the tires varies due to unevenness of the road surface. On bumpy roads, the tires are actually off the road an appreciable part of the time. Every time the tire leaves the road, the friction bond is broken. It is just as necessary to reduce speed on a bumpy, dry curve as on a smooth, slippery curve. Safe speeds on curves depend greatly on the type of curve construction. There are 3 general types of curves: flat, banked, and crowned. The banked curve is the safest construction because the slope of the bank pushes the car toward the center of the curve. This provides part of the force needed to overcome centrifugal force and helps to keep the car on the road. On flat curves, the road push toward the inside of the curve is lacking. Centrifugal force is not counteracted sufficiently and increases so much with increased speed that you have difficulty holding your car on the road. On crowned roads, a car on the outside of the curve tends to slide down the crown and away from the center of the curve. The pull of gravity on the car actually aids the centrifugal force. Only greatly reduced speeds will keep a car that is rounding a crown curve on the road at all. Any moving object has stored or kinetic energy. The greater the speed and the greater the weight, the greater the stored or kinetic energy. This energy is what keeps your car in motion when you disengage the clutch. Kinetic energy varies as the square of the speed, which means that doubling the car's speed will quadruple the car's stored or kinetic energy. Extra speed adds frightfully to the power of your car to do damage. At 20 miles per hour, the force of impact with a solid fixed object will do as much damage as though it fell from a one-story building. At 40 miles per hour, the force of impact would equal that of a car falling 53 feet or from a very high four-story building. At 60 miles per hour, the force would equal a fall of 120 feet or a building 10 stories high. No driver can afford to deal lightly with such potential forces of impact. In order to stop a car, you must use up its kinetic energy. The greater the speed, the greater amount of energy that must be used up. Here is where friction again comes into use. First, the pressure of your foot on the brake pedal causes the brake bands to close around the brake drums, creating a friction drag which is transferred to the tires. This friction creates a back push of the road against the tires. The car comes to rest only when this back push or braking force has used up its stored energy. When a car is going downhill, the problem of stopping is further complicated. You not only have to use up kinetic energy, but you have to overcome the gravitational pull as well. So your braking force must act over a greater distance. The steeper the hill and the heavier the car, the greater the force that is pulling the car downhill. Brakes should be kept in proper adjustment. If one brake takes hold more than the others, it will cause a skid. Friction force is working harder on one side of the car, which allows the kinetic energy to pull the car out of line. Take care of your brakes so they can take care of you. Now let's see what happens when we combine our reflexes with our speed. With an average reaction time of 3/4 of a second at 20 miles per hour, you will travel 22 feet before you are able to apply the brakes. At 40 miles per hour, you will travel 44 feet, and at 60, you will travel 66 feet. In other words, if your speed is doubled, your reaction time distance is also doubled. Braking distances increase as the square of the speed. The car's kinetic energy must be used up by braking force. At 40 miles per hour, the distance is 4 times as great as at 20. At 60, it is increased 9 times. These are mathematical laws of driving that you can't beat. Your reflex time may be slowed down several times by fatigue. Driving efficiency falls with increasing fatigue, and you may doze off, resulting in a fatal crash. In addition to reflexes being slowed down, your vision is impaired by fatigue. It is difficult for the eyes properly to focus on distant objects. A danger zone always extends ahead of you. This is the distance within which you cannot stop. As the reaction time of the driver increases, the danger zone lengthens. As the speed of the car increases, this zone of danger stretches out much farther. Road conditions and brake conditions can make it still longer. The danger zone should never be allowed to become greater than that distance ahead which you are sure is clear of hazards. This is especially true of night driving. Each time your eyes meet the headlight glare of an oncoming car, your ability to see is reduced. Your visibility zone may be only 50 or 100 feet, while your danger zone may extend 300 or 400 feet. The combination of our physical limitations plus the laws of nature prevent us from exceeding a safe speed. We can evaluate approaching hazards only a few hundred feet ahead, and at 60 miles an hour we are approaching disaster at the rate of 88 feet a second. The laws of nature cannot be broken without immediate punishment.